We have a circuit set up here. This is going to be a more challenging problem. We have a power source and 3 resistors, but the information we're given is very slim. Now this is a solvable problem, but we really need to be intentional about how we use our rules for circuit analysis to do so. So the first thing we need to do is say, is this a series or a parallel circuit? Well, we have our resistors one after another. The voltage is going to pass through each of them one at a time. So that would be a series circuit. So we know that this is a series circuit. So what are our rules for series circuits? Well, if we remember, our voltage in a series circuit, our total voltage, is going to be equal to the voltage used up at each resistor. So I've got VR1 plus VR2 plus VR3. Okay, well that makes sense. I'm given VR2 here. That could be helpful. What about current? How do we find current in a series circuit? Well, in a series circuit, the total current is going to be, it's all going to be in one line. So it's all got to flow together. So it's all going to be equal to each other. The current at R1 is going to be equal to the current at R2 and R3. So I total really equals IR1 equals IR2 and equals IR3. All right, what's the last rule? What's our resistor rule? Well, total resistance, it's going to be just like total voltage. So we're going to have R1 plus R2 plus R3. And then what's our relationship between these three things? The relationship between our totals and each of the values at each of the resistors? Well, it's just going to be Ohm's law. It's going to be voltage is equal to IR. Okay. With all of that said, we can start knocking some of these out right off the bat. Look at the currents. Since they're all equal, I'm given the total current. Well, that's going to be the same at each of these resistors. So each resistor is going to have 10 milliamps of current. So I can write that in. 10 milliamps for each one. All right. Now what else does that give me? Well, I've got 20 volts at R2, and I've got 10 milliamps at R2. So if I bring out my calculator, I should be able to use Ohm's law to find the resistance at R2. Should be no problem. Let's do that. So bring out my calculator, and I'm going to take my resistance. To find my resistance, I'm going to need to take V equals IR and rearrange it to equal resistance. That means I'm going to divide both sides by I. And so I'm going to take my voltage divided by my current equals my resistance. So my voltage is 20 volts, so 20, divided by my current, which is 10 milliamps. Now be careful, we need to use amps when we calculate that. So I need to put 0.01 for milliamps. Enter, and that's going to give me 2E3. So that's going to be 2E3, R2 means 2 k ohms. Okay, because that's 2e to the third ohms, which is kilo ohms. All right, well, what's next? Well, let's see, R3. Can I find R3? Well, I don't have R3. I have the current, but I'm still missing the voltage, so I can't do anything with that. But I do have my total resistance, and now I have two of my other resistances. So I should be able to use that, my resistance law, don't mind that, my resistance law to find my resistance at R3. So R total is going to be equal to R1 plus R2 plus R3. RT, our total, was 10 kilo ohms. R1 is 5 kilo ohms. R2 is 2. I'm running out of space here, so plus R3. So all I need to do is take 10 minus 5 minus 2. I can do that in my head. What does that equal? 10 minus 5 is 5. 5 minus 2 is 3. So R3 has to equal 3 kilo ohms. All right, well now I can find my voltage at R3. So what's that going to be? Well, that's going to be, let's make the division right there, V equals IR. I don't have to do any arranging. I just take my 10 milliamps times my 3 kilo ohms. So 0.01, remember, I need to use amps in this equation. So 0.01 times 3,000. Remember, I need to use ohms in this equation, so I need to convert that K to 3 zeros. When I hit enter, I get 30 volts. 30 volts. Okay? Then what should be my voltage at R1? Well, I can do the same thing, 0.01 times 5, and I can already see the pattern here. 3K is 30 volts, so this is going to be 50 volts. And then total voltage, well, that's just going to be my VR1 plus VR2 plus VR3. What's that going to be? 50 plus 20 plus 30? That'll be 100. 100 volts. So we were able to go through and with very minimal information, just a little bit, just these few values, we were able to use just our simple rules for examining a series circuit to find everything else about this circuit. So that's really nice. Let's look at another one. We've got another circuit set up here. This one is going to be just as challenging as the first one. Our first step is to figure out if this is series or parallel. And we can see that all of our resistors are lined up in their own unique branches. They're all lined up next to each other. So they're really in parallel lines. So we can see that this is a parallel circuit. We know that the way a parallel circuit works is that this power source, this voltage source, is connected to each resistor individually. All three of these are connected to the same point. So they're all going to see the same voltage. So let's go ahead and label this circuit and start writing out our rules. So we've got a parallel circuit. It doesn't start with an R, it starts with a P. Parallel circuit. And our voltage in a parallel circuit, because this voltage source is hitting each one of these equally, it's always going to be the same. So our total voltage equals our voltage at R1 equals our voltage at R2 equals our voltage at R3. All right. Now our current, this time, this is going to be the difference in parallel and series. This is really going to drive it home because our current here, it's like we've got one main line where all the current has to flow through, and then it splits up into these three separate parts. Imagine a river flowing that then had to split up into three tinier rivers and then merged again at the other side. So our total current is going to be the addition of our current between each of these branches. So I total equals IR1 plus IR2 plus IR3. It's going to be the addition of each of those. Now what about our current? Now this is the weird one. I want to take a minute to explain why this one is weird. Let's look at Ohm's law for a second. V equals IR. Now, the resistance is really going to be defined by the voltage divided by the current. So let's rewrite that. V over I equals resistance, okay? That's really what resistance is. It's resisting the flow of current, and the current is going to flow more if the voltage is more. So in a series circuit, my voltage is the constant. It's the thing that's really driving how much resistance I have. So when I have a series circuit, it's really all about the voltage. And then my current goes on the bottom. So if I had, this was my total, and then I had the same thing, I've got another Ohm's law at my R1, all of these would add up. I could have the same thing, V over I equals R2, my V total, my V at 1, my V at 2, same thing. But this I is going to be constant. That's going to be the chief difference here. Really, it's because the I is in the denominator, because it's constant, which should make sense because we're basically adding up. It's like if we had 1/2, 2 halves, 3 halves. Well, we need our denominator to all be the same. So when we add up our voltages, or our resistance, it's all going to add up according to what's in the denominator. And in a series circuit, the current's going to be in the denominator. So our resistance is all just regular. What about in a parallel circuit? How does that change? Well, in a parallel circuit, our voltage is going to be the thing in the denominator. So let's look at how Ohm's law rearranges itself. So if I take V equals IR, but now I need the voltage in the denominator, because it's going to be the voltage that stays the same. It's going to be the voltage that's that constant denominator. So how do I get the voltage underneath? Well, let's take a look. First, let's get the current on its own, because I know the current is going to go on top. So divide both sides by R. So now I'm going to have V over R equals I. And then to get the voltage on bottom, divide both sides by voltage. And so now I'm going to get 1 over R equals I over V. And if I did this for each resistor, so if this was my total resistance, this is my total current, well then I'd go 1 over R, 1 equals I1 over that voltage. And that voltage is going to be constant. You might be able to see where I'm going with this. I take 1 over R2 equals I2 over voltage. So really, for my resistance now in a parallel circuit, I have to add these two together to equal my total resistance. So I need to add the reciprocal of each resistance, and it's going to equal the reciprocal of my total resistance. So if we write that out, to find my total resistance, I'm going to go 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. But I don't want to find the reciprocal of my total resistance. I want to know the actual total resistance. So how do I get this 1 over on the other side? Well, the way to get rid of a reciprocal is you take the reciprocal. So I just divide everything by, I divide 1 by everything. So I'm going to put everything under 1. So I'm going to divide by 1 and put everything under 1. And when I do that, these cancel out. And then I rewrite this as RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So I hope by going through that, I've shown you why this version of our total resistance makes more sense for a parallel circuit. And why, even though this looks like a weird equation, it actually really follows logically. So let's use these. I'm gonna actually erase this and rewrite it. And then we're gonna use all of these to go through and determine our values here. Okay. Now that we've got everything written out, we've got all our rules, we can start putting everything into place. So the first thing I see is that I've got a total voltage. And my total voltage is going to be equal to the voltage at each resistor. So I'm going to go ahead and write in that 50 volts in each of my voltages. So 50 volts here, here, ooh, that's not 5, here, and here. Okay, next, let me go through and try and find my resistances wherever I can. I've got a current of 2.5 milliamps at R2. I've got a voltage at R2, so I can use Ohm's law, V equals IR, to find the resistance at R2. So let's go ahead and do that. So it's going to be voltage divided by current will give me resistance. My voltage is 50 divided by 2.5 milliamps. And again, that's milliamps, so it's actually 0.0025 amps. So it's 0.0025. And that gives me 20 E3. And this is why I like engineering notation on my calculators, because now I can just go 20 kilo ohms. There we go. Now R3, how am I going to find R3? I really don't want to have to go through this direction. So instead of I could find R total first, but I don't want to have to work backwards using this. So I'm going to use my total current. I'm going to find my current at IR1, and then I'm going to find my current at IR3. Those are easier equations. That's an easier way to go about it. I'm going to do that. So to find my current at IR1, I need to use Ohm's law again. This time I'm looking for current, so I'm going to divide both sides by resistance. So this version of Ohm's law, I'm going to take 50 volts divided by 50,000 ohms. We might already be able to see what that's going to come up with, but 50 divided by 50123. Okay? And that's going to give me 1 e to the negative third, which is going to be milliamps. So that's going to be 1 milliamp. All right? Now remember, my current in a parallel circuit is going to be the addition of each one. So I've got my total of 11.2. I've got my individual ones. So I can take 11.2, subtract 1, subtract 2.5, and I'll be given the current at R3. So let's go ahead and do that. 11.2 minus 1 and 2.5. And that leaves me with 7.7 milliamps. Okay, so now that I have the current at IR3, I can easily find my resistance at R3 by taking that 50 volts divided by 7.7, just like we did before. So 50 divided by, and now over here I had milliamps, so I didn't have to put in my zeros because they're all the same exact unit. But now I'm going to need to make sure I do that because I need this to be in amps in order to use it in Ohm's law. So I've got 50 divided by 0.0077. And that gives me 6.49. We'll round that to 6.5. So R3 is going to be 6.5 K ohms. All right. And now I want to go through and use this so that we can get the example of what it looks like to use this equation for resistance, but I don't need to. I could just as easily use Ohm's law, take 50 divided by 11.2, and that would give me my total resistance. But I want to at least practice using this equation for resistance. So, in order to do that, I need to take the reciprocal of each of these reciprocals. So what I'm going to do is I'm going to put that in my calculator. It's 1 divided by, and I'm going to put in parentheses, 1 divided by 50K, 1, 2, 3, plus 1 divided by 20K, 2, 0, 1, 2, 3, plus 1 divided by, then 6.5K, so 6500. Put another parentheses. And we can see my calculator is very nice, and it shows me when I input it correctly. So it's 1 over, 1 over, 1 over, 1 over. And so our result is 4.46. We'll round that to 4.47. 4.47 K ohms. Oh, that's not an omega. Okay, 4.47 K ohms. Now notice, I really like my students to notice this, that this total resistance is lower than any of these individual resistances. And that should make sense because my current is greater than any of my individual currents. So it has to be lower to fulfill Ohm's law. But it also makes logical sense because if we look over here, my voltage is allowing current to flow through each of these. So even when R1 has this really high 50,000 ohms, an electron, if it comes over here and sees, this is too long of a line at R1. I really don't want to have to get into the mall through this way. I don't want to wait in line forever. I wonder if there's an easier way to get in. R2, R3, they're easier to pass. So even though this is a really high resistance, it's still able to just go over here and move through one of these. And that lowers the total resistance. It's like having a large building that has a lot of doors. You can have really small doors, but because there's so many around the building, a lot of people can still get in. It works the same way. So hopefully you can see how this equation for resistance makes more sense. You can see how this total resistance really makes sense according to Ohm's law and just according to logic. And hopefully you can see how the currents should be adding up in a parallel circuit and how the voltages should be adding up in a series circuit. Thank you.